everyone. We are today talking about a new learning target on enthalpy. Don't get confused when we talk about enthalpy and heat because we're going to see down here later that they're kind of interchangeable. Okay, so when we talk about enthalpy, we actually mean the heat content of a system. And we're talking about that heat content at a constant temperature. And remember when we were actually talking about heat, it's the energy transfer due to temperature differences, okay? That was heat. Enthalpy, we're talking about constant temperature, okay? This is something that cannot be measured directly. And our symbol up there that you can see, the symbol for enthalpy is capital H. Now, we cannot measure this directly. However, we can measure we can measure a change in enthalpy, which is our delta H, okay? So we can't really measure H, we can measure that change in enthalpy. And this is heat change that occurs during a chemical reaction, okay? You can it makes a lot of sense that we actually call that the heat of reaction. So the heat change during a reaction is called heat of reaction, all right? And sometimes you'll see it written, oops, that didn't show up very well. Heat of reaction, okay? So the change of heat of reaction. This is measured in kilojoules, just like our Q was. Remember when we were talking about heat? Just like Q was measured in kilojoules, so is delta H, okay? Thank you. The way that we measure this, because I said that we can measure our change in enthalpy, is through calorimetry, okay? If you remember, that's also how we measured Q, okay? Why does that make sense? We see that our delta H is equal to the heat, or the enthalpy of products minus the enthalpy of reactants, okay? And I'm going to kind of explain that a little bit lower too. That delta H is equal to Q at a constant pressure. Since everything that we're going to be talking about in our class, all the reactions are at constant pressure that we're talking about, we can say that delta H is equal to Q, okay? So, how we're looking at this little equation. Remember that we talk about Q being either positive or negative, okay? We talk about delta H also being either positive or negative, okay? So how we figure this out is if the heat of products is greater than the heat of reactants. Now remember, we're not calculating these. But if that's true, that the enthalpy of products is greater than the enthalpy of the reactants, are we going to have a positive or a negative change in enthalpy? Let's see. I have an example down here. Let's just say that if the products is greater than the reactants, the products is 2,500 joules, the reactants is 1,500, okay? Products minus reactants, you can see here that we get positive 1,000 joules. So our delta H here is positive. If Q is positive, and if delta H is positive, right, they're interchangeable here, is this an endothermic or an exothermic reaction? Hopefully, you said this is an endothermic reaction because what's happening is heat is being absorbed here, okay? So heat is being absorbed, we have a positive delta H.
Yeah, the heat, remember, is going from the surroundings into the system.
Mm-hmm. Now, I didn't do an example for the second one, but the opposite is true. If heat of reactants is, why did I do that? If heat of reactants is greater than the heat of the products, right, heat of reactants is greater, then we're going to have a negative delta H. And hopefully you see that then this is, oops, I'm just writing everything wrong right now, is exothermic, okay? So think about these being swapped. 1,500 minus 2,500 would give us a negative 1,000 joules as our delta H. Okay?
And that means that we have an exothermic reaction. There is more energy in our in our reactants than there is in our products. So energy is going from system to surroundings. Okay. So we are going to translate this idea of enthalpy and change of enthalpy and heat of reaction to our balanced chemical equations that we know and love already. So I'm just going to talk a little bit about and give you some examples of balanced chemical equations and balanced thermochemical equations. You'll notice that balanced thermochemical equations on that side of the board look very similar to balanced chemical equations, except they also include energy heat in the form of energy in the form of heat in kilojoules, okay? So that's where the thermo comes in. So if we have magnesium metal reacting with oxygen gas, we get magnesium oxide. This is our normal balanced chemical equation that we know and love. And if we have this and we are including our change in enthalpy, or heat of reaction we call it often, we just add in our energy on either a product or a reactant side. Now, I'm telling you that this is an exothermic reaction, meaning there is energy that is being released. So that is why an energy is a product, right? Energy is a product. So we have our magnesium metal. Oh, I wrote it right here. You can write it again. Okay, so energy is a product, right? And so we have 1,203.6 kilojoules that are being released during this reaction, leaving our system to our surroundings. Now, there is more energy in these bonds added all together than there is in these bonds added together, because the total energy of our reactants and the total energy of our products has to equal 0. Mass is neither created nor destroyed.
Energy.
Well, mass too.
Mass too.
Energy is neither created nor destroyed. Jesus, guys.
We're killing this.
Okay, it's like way too late for us to be doing this. Another way that we write these thermochemical equations is just by not actually including it in the actual equation, and we just write delta H equals whatever our heat of reaction is. So if we have an exothermic reaction, we are releasing energy. Our delta H is negative. So for this example, delta H would equal negative 1,203.6 kilojoules. Okay? For an endothermic reaction, our example is aluminum oxide is decomposing into solid aluminum metal and oxygen gas. Now, I'm telling you, this is an endothermic reaction. And so our energy is actually a reactant, okay? Energy is going into the system. So we have our aluminum oxide. It takes some energy to break it down, actually, into our two products. So again, because energy is going into the system, this is a endothermic reaction. Our heat of reaction is positive. And so if we wrote it in our second format that we often see, our delta H, we just have our balanced chemical equation, and then on the side we would have delta H is equal to 3,352 kilojoules. Now, it's important to note that we've been kind of dealing with joules with regards to Q equals MCAT, but now today when we're talking about chemical reactions, there's a lot of energy stored in those bonds. And so when we talk about chemical reactions and thermochemical equations, we're actually going to be in kilojoules always, not almost, always. Okay, so now a little test to see if we actually understand this. In an exothermic reaction, energy stored in the reactants is greater than or less than energy stored in the products.
Pause.
Yeah. Okay, so in an exothermic reaction, energy stored in the reactants is actually greater than energy stored in the products. I got it specifically for this. Is greater than energy stored in the products, because energy is a product, okay? Or heat is a product. In an endothermic reaction, energy stored in the reactants is greater than or less than energy stored in the products. So actually, in an endothermic reaction, we are going to have energy going into our system, and so there's going to be more total energy stored in our products than we're in our single reactant in this case.
Really late right now. All right. Who's ready for some stoichiometry? I know you're all so excited for this. We've been talking about a couple different stoichiometry examples. When we were in gas laws, we're talking about gas law stoichiometry. Now that we're talking about thermochemistry, we're going to do some mass energy stoichiometry involving our heats of reaction. Okay? Now, some hints in order to do this. Same thing with all stoichiometry. We need a balanced equation. Make sure that your equation is balanced. Second thing is, just like stoichiometry in any other scenario, we're going to go to moles first. Remember mole island. We want to get to moles first, and then we can branch out to figure out the energy. Now, the trick here instead of using a mole to mole ratio, which we were doing with stoichiometry, we're going to be using a mole to energy ratio. So notice here the energy is part of our equation. So we're going to use a mole to energy ratio. All right?
So our first and only example, I'm sure you're thankful of that, is to calculate Q when 45.0 grams of calcium hydroxide are produced in the following reaction. And we have calcium oxide reacting with water to form calcium hydroxide, solid calcium hydroxide. Now remember we talked about how we're going to kind of interchange Q and H. This is an example, like we are talking just about that energy that is produced there at the end. It might be referred to, the actual delta H is for the balanced chemical equation, but Q is going to be the energy that is released when we actually have 45.0 grams of calcium hydroxide. So Q, that's going to tell us the heat that is released. So if delta H is 65, is a product, what is it equal to? Negative 65.2 kilojoules or positive 65.2 kilojoules?
Pause.
Okay, it is a product, so it is equal to negative 65.2 kilojoules. Okay, therefore our reaction is exothermic or endothermic. You decide. Pause again.
I know that's funny to me.
It is a exothermic reaction because energy is leaving our system into the surroundings. Okay, that's all we have.
I'm sorry.
Okay.
All right. You're gonna write. Okay, so what are we starting with here? Just like any stoichiometry, we need to find what our starting point is. Our only given is 45.0 grams. And do we need to write CaOH2? Of course we need to write CaOH2. All right, now, stoichiometry, we're going to set up our train tracks. All right, on the bottom, we're going to need grams of CaOH2 because grams is going to need to cancel out. Remember, always go to moles first. That's going to put moles on top. Okay, so we've met our two first hints. All right, so our equivalency statement, hopefully you remember, 1 mole is equal to the molar mass. So we have 1 mole. And the molar mass of CaOH2, we've already figured out for you, is 74.10 grams of CaOH2. Now, grams is canceled out from our top and our bottom. Now we're in moles. Now, here's where instead of the mole to mole ratio, we're going to use a mole to energy ratio. Moles of CaOH2 has to go on bottom so that moles cancels out. What's going to be our unit for energy? Well, the only unit we're given here, kilojoules. Okay? Now, equivalency statement. In 1 mole of CaOH2, right, we have 1 mole here, we have 65.2 kilojoules released. But remember, we said that delta H is negative. So we have negative 65.2 kilojoules. Okay?
Right.
Now moles cancels out. And we're left with kilojoules. Okay, so we're going to multiply across the top. We're going to divide across the bottom. And we get negative 39.6 kilojoules. Correct sig figs are important here.
Okay, so we are calculating Q. Okay, yeah.
That's it.
So
Here's
we
our
would
Q.
say 39.6 kilojoules are released. Right? We might, so yes, this negative sign is telling us that the reaction is exothermic and there is energy leaving the system to the surroundings. But remember, like we talked about in class, that means that 39.6 kilojoules are released.
Not absorbed. That's it. Good night.
Oh my God.